Simple harmonic motion is something that you see all the time, whether you're looking at a cuckoo clock or you're being hypnotized by someone. Simple harmonic motion is not just limited to pendulums, but it's also a mass oscillating on a spring. So let's say we have an object moving in a circle, and this object is a certain distance r from the center of its motion. First, let's plot out its x position. It's going to be at an angle theta at our reference line. And to get that x position, we would go r cosine theta. But now let's say that this object is actually moving in this circle and its position is changing. Its function would be r cosine omega t, where omega is angular velocity. Angular velocity is not that different from the types of velocity that we've discussed before. Its units are radians per second, and it describes how fast an object can cover a 360-degree circle, or 2 pi radians. It does this in a period t, kind of like velocity in meters per second. So here we have our object moving in a circle before, but now a light has cast its shadow against the wall. I plotted its position here, and we can see that it is sinusoidal, and the velocity is the derivative of that position function. So you can see from this position function that there are some moments when the velocity is at a maximum, and there are some moments where the velocity is zero. This all occurs because of energy and its conservation during simple harmonic motion. First, let's talk about pendulums. Pendulums have an equilibrium position when they are just hanging. They also have a length L, and there is always a driving force back to that equilibrium position, which is gravity. At that equilibrium position, we have max kinetic energy. At the amplitudes, we have max potential energy. So here we have a pendulum being brought out to 15 degrees. It swings back and forth, and this is an ideal pendulum, so we're not going to lose any energy. I'm going to time the period, and we can see that it's around 2.8 seconds. Its length is L. If I alter gravity, for instance, we're on the moon, we see that the period goes up dramatically. This relates back to the period of a pendulum equation and how period of a pendulum is indirectly related to gravity. If gravity goes down, for instance we're on the moon, period goes up. Here I am increasing L. Length and period are directly related. So if I increase L, our period should go up. We can time that here. Springs also have an equilibrium position. This is where the spring is no longer stretched. Now, if I pull this spring out and I release that mass, I am now at an amplitude, and at the amplitude I have max potential energy. Here my potential energy is due to the elastic. At the equilibrium position, I have max kinetic energy, just like with the pendulum. Now let's look at a pendulum that is vertical. We still have a hanging mass, and if I release this mass, I will stretch the spring. I start with only gravitational potential energy, and I end with only elastic potential energy. At the amplitudes, again, I only have potential energy, and it's at a maximum. I also have an equilibrium position where the weight equals the elastic force. At this equilibrium position, I have max kinetic energy. Here I have some springs, and on spring 3 I can change the spring constant here with this softness scale. I can decrease or increase the spring constant. I'm going to add a mass, and we see that the spring stretches, the mass oscillates back and forth according to simple harmonic motion. Now, if I change the spring constant, if I increase it, making the spring harder, the mass oscillates back and forth, but now at a much faster rate. This increase in the spring constant has decreased my period, which means they are inversely related. If I lower the spring constant and add the mass, the spring stretches much further, has more distance to cover, and the period increases. So this shows that the spring constant and period are inversely related.